Hi everybody, welcome back to chemistry class. Today's the learning objective is about the basic concepts of the organic chemistry. Coming to the basic concepts of the organic chemistry, we need about the bond polarization or the electron displacement or the electron redistribution. The bond pair is equidistant from the centers of the two bond nuclei, that is homodiatomic molecules like hydrogen, hydrogen, chlorine, chlorine. For such type of molecules, they are the pure covalent compounds. And the bonds are pure covalent bonds. In heterodiatomic molecules, the bond pair it is not equidistant from the center of the nuclei. For the two bonded atoms, the electron pair it is slightly shifts towards the more electronegative atom. I'm repeating, in heterodiatomic molecules, bond pair is not at equidistance from center of nuclei of two bonded atoms. The electron pair, the bond pair, shifts towards the more electronegative atom. This is due to greater attraction it takes place. Such bond polarization or electron redistribution takes place or the electron displacement is observed. So, depending upon the factors that there are different factors that are affecting this electron availability. The more electronegative atom acquires partial negative charge and the less electronegative atom gets partial positive charge. Such bond polarization takes place. So such type of molecules are called as the polar molecules. The bond polarization is indicated by arrow mark. Tail indicates the partial positive charge and the heat and the remaining one is the partial negative charge. For example, in HCl molecule we'll take chlorine is more electronegative. Hence, the electron attraction tendency is more towards this chlorine atom. The bond pair is near to the chlorine atom and the hydrogen gets the partial positive charge and the chlorine gets the partial negative charge. So the molecule, because it's of polarity, takes place. The polarization can be known through dipole moments. The dipole moment is represented by mu. Now let us see the factors affecting the electron density. As I've told you, for HCl molecule may affect the reactivity of the molecule. It changes the nature of the compound which reacts with the reagent. Similarly, one more example. Before explaining the factors affecting the electron availability, we'll see the effects, inductive effect, electromeric effect, how these are governing the reactivity of the molecules. For example, OH does not react with high electron density molecule or position, but it easily reacts with the low electron density molecule. Similarly, the positively charged E reacts with high electron density molecules. Many such factors which affect the reactivity were recognized for us. In that, see, there are many factors which affect the reactivity. The factors which are affecting the reactivity, electron availability, is inductive effect. It is the inductive effect. The second one is the mesomeric effect or the resonance effect. And the third one is the hyperconjugation. So now I'm going to explain you about the inductive effect. In a covalent single bond between unlike atoms, as I've told you, HCl, the electron pair that is forming the sigma bond is near. It's never shared the shared equally between the two atoms. It tends to attract it towards a little more towards more electronegative atom. For example, HCl, I've told you in that HCl it is attracted towards the chlorine atom. In alkyl chloride, the electron density it is attracted towards the chloride than the carbon. It is due to the more electronegative nature of the chlorine. So the sigma here, what you have to understand is if sigma electrons are involved in affecting the electron density, it is inductive effect. If sigma electrons are involved in affecting the electron density, it is known as inductive effect. If in a carbon chain, if different electronegative atoms or groups are present, they create a positive or the negative charge on adjacent carbon atom. This positive or negative charge created induces the adjacent carbons. This is called inductive effect. The positive or the negative charge that are created induced on the adjacent carbon atoms. This is inductive effect. There is induction. Here you can see the charge is induced, so it is inductive effect. It's a permanent effect in a molecule. This effect is decreased if the distance between the atom increases. Along the carbon chain, it increases. The effect is zero at the fourth carbon atom. So the difference in the electronegativity causes this polarization in the covalent bonds. And this polarization, it is responsible for acidity, basic behavior of many molecules. You can explain the acidic behavior. We can explain the basic behavior for the organic molecules. The electron distribution in sigma bond is known as inductive effect. Electron distribution in sigma bond is known as inductive effect. I'm repeating. The electron distribution in sigma bond is known as inductive effect. It's permanent effect applied till third carbon of the carbon chain in a molecule. And the dipole moments of the molecules are predicted with the help of this effect. This effect it is decreased if the distance between the atom groups increases along the carbon chain. And if the compound is having more than 4 carbon atoms, this effect becomes zero at the fourth carbon. In the above, we can see different examples. So if you take N-butyl chloride in that example, N-butyl chloride, if you take for instance, I'm giving here, it's not written, but I'm giving you the example. You take a butyl chloride. You're having 4 carbons and a chlorine. In this example, chlorine is electronegative atom. Carbon 1 creates partial positive charge for the adjacent carbon. And C1 carbon becomes less electron rich. Hence, it's become more electronegative than C2 carbon. So, carbon 1 creates some partial positive charge on C2 carbon. Similarly, C2 creates some partial positive charge at C3. Therefore, after that, there is no observable effect at C4. In fact, this effect decreases from C2 to C4. This effect will decrease from C1 to C4. I'm repeating. For example, if you take a butyl chloride, example not given, just for I'm explaining you. You take a butyl chloride, CH3, CH2, 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 CF. In the above example, chlorine is more electronegative than carbon 1, which is attached to chlorine carbon, which is attached to the chlorine atom. So it creates a partial positive charge for the adjacent carbon. Chlorine gets the negative charge, partial negative charge, and the C1 gets a partial positive charge. And C1 is more electron rich compared to the C2 carbon. It is more electronegative than C2 carbon. From chlorine, C1 is less electronegative. And from C1 compared, C2 is getting less electronegative. And C1 is more electronegative. So C1 creates partial positive charge on C2 carbon. Similarly, C2 atom creates some partial positive charge at C3 atom. So after C3, there is no effect. It decreases. So if groups like chlorine attract the electrons towards themselves by inductive, groups like chlorine attract the electrons towards themselves by inductive effect. Consequently, they induce partial positive charged carbon atoms. Consequently, here they induce a partial positive charge at the carbon. So this effect is electron attracting inductive effect, or you can tell minus I effect. If chlorine atoms attract the electrons towards themselves by inductive effect, they induce positive charge at the carbon atom. So this effect is electron attracting inductive effect or minus I effect. This effect, it gets decreased, it moves towards from chlorine and gets stopped at C4. It is indicated by an arrow mark. And the covalent bond, if you have an arrow, in the covalent bond, if you have an arrow mark, that is the indication for the inductive. The head is towards the atom which attracts the electrons. If attraction is more, one can use more number of heads. If attraction is more number of heads can be used to show the higher effect. The minus I effect present in the N-butyl chloride can be shown as follows. See, in minus I effect, electron withdrawing element or the element with higher electronegativity than carbon is attached to the carbon atom. Carbon is attached to the carbon. The carbon atom to which the group is directly attached is called alpha carbon. And the carbon which is attached to the next to the alpha is beta carbon. And the third one is the gamma carbon. So inductive effect operated till gamma carbon, only till third carbon. As I have told you, it is extended only to third carbon, that is gamma carbon. Due to this effect, you can see acidity of the hydrogen. What is an acid? Which gives H plus ions. So the losing of H plus ions is more. So this effect will increase the acidity of the H plus ions, which is attached to the carbon. Because this bond, it bonds between the carbon and the hydrogen. It makes weak and the hydrogen removal becomes easy. Why the H plus ion is lost is this effect, why the acidity is increasing. It is because the hydrogen is attached to carbon, and because it is bonded between carbon and hydrogen, hydrogen is more positive than carbon. It becomes weaker and hydrogen is lost. Once if the H plus ion is lost, then that is the acidity. Okay. So in minus I effect, a electron withdrawing element or the electron with higher electronegativity than carbon atom, in minus I effect, electron withdrawing element or the element with more electronegativity compared to carbon is attached in that compound. The carbon atom to which the group is directly attached is alpha carbon, and the carbon next to the alpha carbon is the beta carbon, and the carbon next to the beta carbon is, that is the third carbon, is gamma. So you can observe the inductive effect till gamma carbon only, and due to this effect acidity is increased. The H plus ions are lost from that molecule which are attached to the carbon atom. So here, because the H plus ion, it is more positive and it is lost as it has become weak. So the acidity is increasing. Now, in plus I effect, we'll see in plus I effect. In plus I effect, the electron donating group is attached to carbon. So in minus I effect, electron withdrawing group is attached. In the plus I effect, how it causes is due to the electron donating group. It's a carbon atoms. I'll give you the examples of these donating groups. And whose negativity is lesser or similar to that of carbon. It donates, it supplies electrons to the carbon. It stabilizes the carbocation formation. See, carbocation means carbon is having the positive charge. This carbocation, it is getting stabilized. Yeah, the positive one means it is getting stabilized by accepting the electrons. So the donating group gives the electrons and this carbocation gets stabilized. So this effect, you can predict the stability of intermediates formed in the organic reactions. Different organic reactions will be seeing. In that organic reactions, will be having carbocation, carbanion, free radicals, so on will be formed. And the stability of these carbocations, carbanions, free radicals can be explained. Okay? And the groups which are responsible for the minus I effect are called minus I groups. The groups which are showing minus I effect are nitro group, cyanide group. Nitro group is responsible for more minus I effect. Then cyanide, then COH group, and fluorine group, chlorine, bromine. Okay, I'm giving you the examples of minus I effect groups, minus I groups. The group which is responsible for minus I effect are the minus I groups. Nitro group, cyanide group, COOH group, fluorine group. Okay, fluorine atom F minus, chlorine atom, bromine atom, iodine, iodide, bromide, chloride, fluoride, OR, OH, C6H5. All these groups are the minus I groups. In the minus I group, you can observe the atoms are from 5th group, 6th group, 7th group. Nitro group, you're having oxygen. In the cyanide, you're having nitrogen. In the acid group, you're having oxygens. So nitro group, nitrogen, it's of 5th group. Oxygen, 6th group element. And coming to the 7th group, fluoride, chloride, bromide, iodide, all these are the 7th group element. So 5th, 6th, 7th are electronegative in nature. So these attract the electrons. In the alkoxy group or in the hydroxy group, you're having oxygens. Even these are having the 6th group element, electronegative oxygen. So an atom or a group that releases the sigma electrons towards the carbon chain, that is, we have told that is the plus I group. An atom or a group that releases the electrons, donates the electrons towards the carbon chain, such effects are called as the electron releasing or plus I groups. Okay, so the carbon atom of the chain gets partial negative charge. It gets the partial negative charge, which is associated here. It gets the carbon atom of the chain gets partial negative charge when they are attached to the plus I groups. The partial negative charge associated with the carbon atom. When an electron releasing group like Z is present in the molecule, so it's nothing but the plus that carbon groups, methyl, ethyl, isopropyl, tertiary butyl. All these groups are the plus I groups. So the carbon atom of the chain gets partial negative charge when it is attached to plus I group. when it is attached to the plus I group. And when the electron releasing group, yeah, I've told you the electron releasing group examples, those are the plus I groups, alkyl group. Your tertiary alkyl group has high plus I effect than the primary group. So the tertiary group is having more donating capacity and more plus I group than isopropyl group. And then primary alkyl group. Sorry. The first one is the tertiary alkyl group. The second one is the, it's not the isopropyl, it is a secondary alkyl group. Example is isopropyl. And primary alkyl groups. All these have the plus I effect, donating capacity. These interactive effects, these were decided by taking the hydrogen atom R3H as standard. When the atom or the group replaces hydrogen from R3CH, decreases the electron density. Such effects are, if the electron density increases, then it is plus I effect. I'm repeating, when a group replaces hydrogen, decreases the electron density, then that is minus I effect. When an atom or a group that replaces hydrogen, it decreases the electron density, then that is minus effect. If electron density is increased by that atom or a group, then that is plus I effect. Okay? And we are having various applications for this inductive effect. First, in the applications, you can, I'll just give you the brief view on the applications. That is, basicity of the amines can be discussed. In the amines, you're having R and H2 group. So you can discuss about the basicity of the amines. Amine act as a base because they are proton acceptors. In amines, the lone pair on the nitrogen or like ammonia, it can donate electrons, the electron pair to the electron deficient. Hence, these are bases. Amines act as a basis because the nitrogen on the nitrogen of the amine, it is having protons. It can donate these are the proton acceptors. Okay, so it can donate the electron pair to the electron deficient substance. So one which donates the electrons is a base. Any group increases the electron density at the nitrogen, increases the basicity. Okay, so simply just remember, basing on this inductive effect, we can explain the basicity of the amines, acidity of the acids. Basicity, here the bases, amines are bases. Why? Because they donate the electron pair. The one which donates the electron pairs are nothing but the bases. We can explain basing on this electrons on the nitrogen here. And in general, plus I group increases the electron density on the nitrogen. R NH2, R is a plus I group. It increases the electron density on the nitrogen. Therefore, the nitrogen easily donates the electrons. The basicity is increasing. Okay, this is the way we can explain the basic nature of the amines. Already the nitrogen is having electrons. Moreover, although it is having nitrogen, if alkyl group is a donating group, so the nitrogen is becoming more rich in electrons so that it can easily donate the electrons. The one which donates the electrons is a base. So basing on this minus I effect, we can explain the basicity for the amines. And similarly, we can explain even the acidity for the acids. For carboxylic acids, okay. So the basicity NH3, CH3NH2, methylamine, dimethylamine, chloromethylamine. Okay. So similarly, tertiary amine, all these are having the alkyl groups attached, and thereby alkyl groups donate the electrons and nitrogen gets rich in electrons, and thereby the basicity is the basic nature of the amines are increasing. So tertiary amine more basic because it is having three alkyl groups. Then secondary amine is basic, then the primary amine, and then primary amine, then ammonium. But the order is slightly there is a change because tertiary amine there is a steric hindrance due to the three alkyl groups on the nitrogen, and thereby the basicity is decreasing. So the secondary amine will have more basic nature. Secondary amine, two R groups will be present. The two R groups donates the electrons to the NH2. And then primary amine. The third comes is the tertiary amine. Okay, this way the basicity of the amines increases. The basicity of the amine can be explained, order of the basicities of. Now, a small instance, that is the acidity of the carboxylic acids will take. Carboxylic acids are proton donors. See, inductive effect, I'm explaining you that I'm just giving you the application, a brief application of the inductive effect. One is the basicity of the amines, and the second one is the acidity of the carboxylic acids. Carboxylic acids are the proton donors. It acts as the acids. RCOOH gives rise to RCOO minus plus H plus ion. So because it is giving H plus ion, it is an acid. The higher bond dissociation of OH in the carboxylic acids, greater is the acidity. Inductive effect affects the strength of the carboxylic acids. I am repeating, inductive effect affects the strength of the carboxylic acids. If plus I group, it decreases the acidity. Plus I group, what happens? More electron density. Thereby the acidity decreases. If minus I group is attached to the acid, if minus I group, it takes away the electrons. Therefore, the H plus ion is released. Okay, if minus I group is attached to the acid, electron density decreases, acidity increases. I'm repeating, the acidity of the carboxylic acids can be explained by this inductive effect. Now, an acid RCOOH is a proton donor, so it acts as an acid. Now, for any compound or for an acid, if minus I group is attached, electron withdrawing group minus I group, acidity will increase because electron density decreases, H plus ion is lost. And for the acid, if plus I group is attached, electron releasing group is attached. Once if the electron releasing group is attached, H plus ion is not lost because there is more electron density. There is no requirement for the electron density. Therefore, H plus ion is not lost. Acidity is decreasing. So simply you remember, if minus I group is there, acidity increases as the electron density decreases. If plus I group is there, electron density will increase and the acidity will decrease. So basing on this inductive effect, we can explain the acidity and the basic nature of the compounds as it's a basis. Basing on this inductive effect, you can even explain the stability of the carbanions, carbocations, and free radical. effects. These are all the applications of the inductive effect. Now let us see resonance effect. What is a resonance effect? See here, this is electron redistribution that takes place in the unsaturated and especially in the conjugated systems. This is through their pi orbitals. You can see CH2 double bond, CH single bond, CH2 plus. Here there is a shifting of the double bond and the positive charge in the opposite direction. Here resonance effect you can see generally the effect in which pi and n, that is lone or the non-bonded electrons, influence the electron density is known as resonance or mesomeric effect. This is generally observed in the molecules having alternate double bonds. Everywhere you can see this resonance effect. All benzenoid compounds or non-benzenoid compounds or the aromatic compounds, we can see here the effect in which pi and n electrons influence the electron density. This is known as the resonance or the mesomeric effect. This is generally observed in the molecules having alternate pi bonds and n electron pairs, non-bonding electron pairs. If a single structure fails to explain the property of the compound, more than one structure can be taken. More than one structure can be taken. More than one structure can be taken and considered for the properties. So these are all the canonical or the resonance structures. These are all the canonical or the resonance structures. Canonical structures are written based on the valency rules. Canonical structures or the resonance structures. Canonical structures and the resonance structures. Here we can see this canonical structures and the resonance structures. Canonical structures are written based on the valence rules. There are different rules for these canonical rules. The position of the atom should not be changed in the structures. The position of the atoms should not be changed in the canonical structures. The number of lone pairs and the unpaired electrons should be same. The number of the lone pairs and the unpaired electrons must be the same. The more the number of the canonical structures possible, the greater will be the stability of the compound. More are the resonance structures, more is the stability. Next, canonical structure should not differ from each other. And the lowest energy or the most stable canonical structure contributes more towards the resonant hybrid structure. Charge separated structures are less stable and contribute to the resonance hybrid. Charge separated structures are less stable and contribute to the resonance hybrid. Charge distribution gives highest stability. This charge distribution gives highest stability to the molecule. The greater the planar structure, the higher would be the resonance effect. The greater the planar structure, higher would be the resonance effect. The energy difference between most stable canonical structure and the resonance hybrid. Energy difference between the most stable canonical structure and here the canonical form and the resonance hybrid is known as resonance energy. Here the energy difference between the most stable canonical form and the resonance hybrid is known as resonance energy. The higher the resonance energy, greater is the stability of the molecule. Canonical structures are separated by the double-headed arrows here. The curved arrows, whatever you're seeing here, curved arrows, are used while writing the structure of the canonical structures. And resonance hybrid, it is the actual structure of the molecule. Okay, so benzene also you can write different structures. So almost for the aromatic compounds, benzoyl or non-benzoyl structures, we can write the structures. Now we'll see what is this resonance effect. Electron redistribution takes place in the unsaturated and especially in the conjugated systems via pi orbitals. And when the double bond and lone pairs are in conjugation with any charge, then the movement of the electron from high density to low electron density takes place. This is called resonance. When double bond or the lone pairs are in conjugation with any charge and the movement of the electron from high density to low density takes place. Yeah, double bond or the lone pairs, they're in conjugation and with any charge, the movement of the electrons from high density to lower density takes place. That is resonance. Previously in the above diagram, you have seen the structure. Actual structure is the hybrid of the canonical form. And that is the most stable canonical form among all the structures. The actual is the most stable structure, most stable canonical form among all the structures. When resonance and inductive both effects are operated in the same compound, then resonance is given preference over the inductive. For any behavior of the molecule, we need the resonance effect, not the inductive effect, or in order to explain the behavior. And like inductive resonance, it can be two types, same, plus psi effect, minus psi effect. Similarly, the resonance provides stability to the charged molecule by delocalization of the charge in conjugation. Now, in the resonance effect, so that is about the resonance effect or the mesomeric effect. You can also call it as a mesomeric effect. Here, the groups which increase the electron density of the carbon atom by mesomeric effect known as electron releasing mesomeric effect or simply plus M effect. Plus M effect. Electron releasing mesomeric effect is plus M effect. These groups will increase electron density at the carbon atom. OH group, bond NH2 group, bond OR group, NHR, primary amine, secondary amine, tertiary amine, alkoxy group, OH group. All these are plus M groups. Now, opposite to this, when the molecules like carbonyl group with conjugation with pi bonds, the carbonyl groups create positive charge on the adjacent carbon atom. Because it takes the carbonyl group is having oxygen, it attracts the electrons, it takes the electron and creates positive charge to the adjacent carbon atom. Okay, for the attracting. Such type of groups are called electron attracting mesomeric groups, minus I groups. If electron releasing group is there, that is plus M group and plus M effect. If electron attracting groups are there, then that is minus M effect and minus M groups. Bond NO2, bond sulfonyl group, nitro group, cyanide group, COOH group, COR group. All these are minus I groups. Even using mesomeric effect, we can explain acidity of the phenols, acidity of the acids using this resonance effect. Now, we'll see what is hyperconjugation. The electron releasing effect of the alkyl group is called hyperconjugation. Sigma bond resonance you call. Sigma bond resonance we call here. How many number of hydrogens are there? They give electrons and they give the stability to the molecules. the electron releasing effect of the alkyl groups, plus I group. It's in the following order. Here, hyperconjugation. See, if alkyl groups are attached to the double bonds, double bonded carbon, carbonium ion, free radicals, electron releasing effect will be in the opposite direction. So the electron releasing effect would be different from the inductive effect. So this effect is hyperconjugation, or you can even call it Baker-Nathan effect. Baker-Nathan effect. The electron, here. We can clearly tell the electron releasing effect of the alkyl groups by the hyperconjugation. It is due to the hydrogens attached to the carbons. How many number of hydrogens are there? That many number, that much electrons are released. Therefore, the stability is more. As the number of hydrogens are increasing, the stability is increasing. Here you're having, you can see, this is in contact. Here you're having, you can get total 4 structures. Okay, so we can get the total 4 structures. Here you can get total of 7 structures. 1, 2. Here these are 3, and here 3. You can get total of 7 structures. And here 3 plus 3 plus 3. So you can get here we can get the 10 structures depending upon the CH items. Here you can get the 9 structures. It's given 10. Here you can get the 9 structures. Here you can get the 7. 3 plus 4. 7 structures. Here it is 3 plus 2. You can get 5 structures. Okay. In this way, as the number of hydrogens, the conjugation, it is a sigma bond resonance, depends upon the number of alpha hydrogens present in the compound. More the alpha hydrogens, more number of way the structure can be written, and more will be the stability. In the given picture, the last structure you can see more stable due to more number of alpha hydrogens. Here you're having 5, here it is 7, and here it is 9. Therefore, more number of hydrogens, CH hydrogens are there, more resonance structures possible, and more is the stability. So this way you can explain the stability of the carbo. Using this hyperconjugation, we can explain stability of the carbonium ions, free radicals, carbanions. All this can be explained. Okay, the delocalization effect is hyperconjugation or Baker-Nathan effect. So this is no bond resonance. We call it as no bond resonance. On the basis of the orbitals overlap also we can explain. So hyperconjugation can be due to the hydrogen atoms attached to the carbon. Okay, so this is called hyperconjugation. It depends upon the alpha hydrogens. So these are the effects which we have studied today. So what are the different effects that are affecting what the electronic effects, the factors affecting the electron availability? We have seen factors affecting the electron availability. These are all the electronic effects. These effects govern the reactivity of the molecules and the chemical reactions. Bond polarization, electron displacement, everything can be explained using these effects. It is due to the electron redistribution. So I hope you have understood today's class. That is on the inductive effect, plus psi effect, minus psi effect. Application part not given in the slide, but I've explained you about the acidity and basicity of the compounds. Similarly, resonance effect and hyperconjugation. Thank you, everybody.